In this video, we're going to talk about solving logarithm equations. So now the types of equations we'll be able to solve, we can solve linear equations, quadratic equations, exponential equations, and now logarithm equations. All right, so we previously learned how to solve exponential equations. We did it using the one-to-one property. Again, that one-to-one word is not super important, but what's important is if you have these two exponentials with the same base, the only way those two things are equal is if their exponents are equal. So if these things have to be equal, then we kind of ignore the a parts and just set the exponents equal. All right, so we get these two exponentials have the same base, and then we kind of ignore them after that. All right, so it simplifies the problem quite a bit. And it turns out logarithms are also one-to-one. So if we're able to get a single log with the same base equal to each other, the only way this is possible is if these insides are equal. So we kind of ignore the logs, and b equals c. All right, so just like we're doing with exponentials, and because exponentials and logs are related, they have some of the same properties, and this is one of the nice ones. All right, a single log equals a single log. We kind of ignore and just look at the insides. All right, so how can we do this problem? All right, well, we have a single log, technically log base 10 when there's no number there. It's not actually important at all. We just see that they're the same logs and we kind of ignore them. 2x plus 1 equals 7. We're going to subtract 1 from both sides, and then divide by 2 to get this x by itself. So x equals 3 is our final answer. All right, next example, pretty much the same problem. A log with some stuff in it equals another log with some stuff in it. That means 2x plus 10 equals 4. Subtract 10, divide by 2. All right, and here's one thing we have to do with logs that we didn't have to do with exponentials. All right, when we were talking about logarithms originally, we learned their domain is all the x values strictly bigger than 0. So whatever we're putting into a log has to be bigger than 0. So one extra thing we have to do with logarithms is check to make sure our final answers make sense in the original problem. This didn't matter with exponentials because we could plug anything into an exponential, but with a log, we have to make sure this makes sense. If I put in 2 for x, negative 6 plus 10, and that's 4. And 4 is fine to plug in, so this answer is fine, and that's our final answer. Oh, that's this whole side. All right, so since logarithms have a limited domain, it's only x is bigger than 0, all right, or the values that we plug in are being 0. Sometimes we get these things called extraneous roots. Extraneous roots are things that look like they should be a solution, but because of some properties of the original function, they're actually not. All right, so for logarithms, all right, make sure you don't get an extraneous root by plugging your answer back in and just making sure the inside of the log is not negative. All right, we can see our answer can be negative as long as it doesn't make it the inside of a log negative. All right, so here's another example. Log of 8 plus log of x equals log of 4x minus 1. We can't just, so the most common mistake I would see students make is their next line would look like this. Because they just kind of get rid of all the logs. You can't do that. In order to do our one-to-one property, we have to have a single log on both sides, and this is the reason we talked about combining and expanding logs and stuff, because we can combine these two logs here. There's a plus sign between them. If there's a plus sign between two logs, we can multiply the insides. All right, so the whole reason we talked about combining logs is so that we can solve equations like this. Now I have a single log on both sides, so I kind of ignore them. I would subtract 4x from both sides and then divide by 4. And now I have to ask myself, does this answer make sense in the original problem? Well, 8's still positive, but if I try to plug in negative 1/4 for x, that'd be putting a negative into this log, and that's bad, right? So I can't plug negative 1/4 in, so this is an extraneous root. I have to cross it out. It's not actually an answer to the original problem. And this problem has no solution. All right, so this will happen sometimes when you're solving log equations. You'll do everything right. All right, everything we did here was right. All right, but because logs are kind of special, you can't plug in everything. All right, sometimes you actually get no solution, even though you found an x value. And this is called an extraneous root. All right, so the general strategy, use logarithm properties until you have a single log on each side. All right, then use the one-to-one property to eliminate the logs. All right, solve the new equation. For right now, it'll just be a linear equation. And then this fourth one we did not have to do for exponentials, so these were pretty much the 3 steps for exponentials. But for logarithms, we have to check for extraneous roots. All right, one more example that I'll do. Again, the first thing is I have to get a single log on both sides. So I have these 2 logs with a plus sign. I combine them into a single log, and I multiply 4 times that whole inside x plus 1. The right-hand side, I also don't have a single log because I have this extra 3 in the front. But again, we have our logarithm rules that allow us to bring this 3 in. 2 cubed. And now we've gotten to just a single log all by itself equals a single log all by itself. I can set the insides equal to each other. All right, now to solve this, I'm going to have to do some simplifying. I can distribute the 4. All right, make sure you don't forget to distribute the 4 in here. And 2 cubed is 8. All right, then I want to get this x by itself, so the first thing I'm going to do is subtract 4 from both sides. Then I get rid of this 4 by dividing by 4. I get x equals 1. The last thing I have to do is make sure this makes sense in the real problem. If I plug in 1 for x, I get 2. And 2 is fine to plug into a log because it's positive. So this is the answer, x equals 1. All right, so here's one for you to try on your own. The only kind of curveball I throw at you is there's a minus sign there. All right, so be careful with that. All right, I'll show you the answer to this problem in 3, 2, 1. All right, so that minus sign turned to division. So in our previous examples, it was a plus sign, gave you multiplication, but remember minus sign between logs is division. Now I have a single log, I ignore them. To get rid of this 5 on the bottom, I multiply by 5 to get 50. And the last thing I did is, does 50 make sense? So if I put a 50 here, that's positive, and it's fine. All right, so here's the quick summary. All right, simplify your equations before using the one-to-one property. So we talked about all those logarithm rules for a reason, so we can combine them into a single log. And then again, this one is real important. All right, make sure you check for extraneous roots. All right, make sure the inside of the logarithm is not negative. One common mistake is students just see a negative answer and they automatically imagine it's an extraneous root. But we saw in this example, you can get a negative answer as long as it doesn't make the inside of your logarithm negative. If I were to plug in -3, the inside's +4, and that's fine. So negative answers are fine as long as they don't make the inside negative. All right, so when you're checking for extraneous roots, it's more similar to this one. If I put -1/4 in here, the inside's completely negative, and that's bad.